All right, the assignment is 5.3. And 5.3 is about connecting the graph of f with the graph of f prime. Emerson, are you paying attention? I want you to connect. So we're talking about this connection between the function of f and the graph of f prime. Okay, before we do that, I want to, this is a connection to what we talked about last time in 5.2. So this does get a little wordy, I apologize, but this is directly from a past AP exam, and so I think it's worthwhile to discuss this as a class. So a particle along the x-axis. Oh, this feels like kinematics. In fact, most of today is physics. If you like physics, that's going to make today a sweet day. And if you don't like physics, well, maybe not then. Okay, so a particle, now the bell. A particle along the x-axis. Sorry, particle along the x-axis. A particle moves along the x-axis. I apologize. A particle moves along the x-axis. So at its position at any time when t is greater than or equal to 0 is given by x of t equals t cubed minus t squared minus t plus 3. Now there's something else in this equation that indicates that this is a position function. What is it? There's something in this equation that indicates that it is a position function. What is it? Miguel?
I guess the time is greater than or equal to 0.
No, that could be, we could be talking about volume or acceleration if it was time greater than 0. Emerson, any ideas?
I'm not too sure.
What about this t of x? Oh, sorry, x of t. Doesn't this indicate position? In fact, there's another notation that's also common for position, and that would be s of t. If it was volume and not position, what would this look like? Emerson? If it was, if it was velocity. If it was velocity, what would it look like? What would this part here look like? It would be v of t. And acceleration? A of t, yeah. So these are common notations right here that we would use when indicating a position function. Okay. So a particle moves along the x-axis so that its position at any time t is greater than 0 is given by x of t equals t cubed minus t squared minus t plus 3 for what values of t for t values between 0 and 3 is the particle's instantaneous velocity the same. That does not look like same. Is the same as its average velocity. Does that, I know it seems wordy, but does that remind you of something that we did last time? Do you remember what the theorem is? It is the mean value theorem. Do you remember, Josh, what the mean value theorem says?
Isn't basically like if the function is continuous on a closed interval and differentiable, then some point will have a tangent line equal to the.
Yep. Yeah, there's going to be a tangent line in there with that will be equal. The slope of the tangent line will be equal to the average rate of change. Yep. That's exactly, this is talking about the mean value theorem. Oops, that's not what I meant to do. Emerson, you just have one more hour.
Sorry.
Let's make this last hour count. This is the last, Emerson, this is the last hour of instruction, of academic instruction for the entire year.
I'm sorry.
Let's make it count. Sasha, do you know how to do this? To summarize the mean value theorem, the mean value theorem looks something like this. That there is a derivative of some value C that is equal to our f of b minus f of a over b minus a. Do you remember that? Does that look familiar?
Yes.
Sure. I'm not saying that's the only place to start, but I think that's a good start. So if we take the derivative of this, that gives us the derivative of a position function gives us what? Maybe that's something that we need to review. Maybe that's something that we need to review. All right, let's talk about here's a graph. And this is time. And this is distance. Now let's say that our graph for this time distance equation looks something like this. How do we read that? How could we read that? What would it say? What is being said here in this graph?
Exponential.
Okay, it looks exponential, but is there a way that we can read it in terms of time and distance? Let's say that this graph represents your distance from home. How do we interpret what's happening here on this graph? Yeah. We can see that as time continues, what happens to the distance? It increases as well. Now it looks like it increases. At first it's increasing slowly. The distance is increasing slowly, but what happens over here? The distance increases a lot faster, a lot faster. What does it mean if I consider the slope at some point like here? Now slope is defined by what? By rise over run. And when I rise from, say, this point here and run to this point here, this would be my rise and my run. The rise is what in units? This would be the rise is, and the run is. What kind of quantity are we talking about that is distance over time? Yeah, distance over time is speed, and in this case, we'll just call it velocity. So we're talking about velocity. The slope of a distance time equation is velocity. One more time, the slope of a distance time equation is velocity. So how do we calculate slope? How do we calculate the instantaneous slope? This is a calculus class. We find the derivative. Here, what kind of function is this? This is its position. It's a position function. It tells me that, and I also know because they're using the x of t. If I'm given a position function, which tells me how far we are from home, that's my position from home, how do I find a velocity function? We take the derivative. So let's do the derivative. The derivative then of this function would be v of t, which equals what? Louder, please.
3t squared minus 2t.
Minus 1. Nice. Who was that said that? Is that Emma? Oh, Ellie. I'm sorry. Ellie. Good job, Ellie. All right. So we found the derivative. Now what? This is what we're trying to calculate. What piece is this?
So that's like, find the after change of part of
Yeah, this is my derivative. So that's this piece here, huh? So we'll just write that out. We have 3t squared minus 2t minus 1. Yeah, we still need to find the average. We need to find the average rate of change that goes here. How do we find the average rate of change? We should be comfortable with this equation, but maybe not how it's written, right? We're probably more comfortable with this equation, the average rate of change, being written like this: y subset 2 minus y subset 1 over x subset 2 minus x subset 1. Yes?
What's the C?
The C value? The C value is whatever the T value is that will equal the average rate of change. That's that moment where these are equal. I don't know what that is yet, because I have to figure out this over here. So do I have enough information here to figure out my average rate of change?
Yeah.
All right, what do I know?
No. I guess what would be your X values?
All right, what are my X values?
0 and 3.
All right, 0 minus 3, okay. How do I find the corresponding Y values? Yeah, let's plug in the zeros here, here, and here. What do we get? Well, yeah, we just get this 3. Everything else falls away. So that would be, we have 3. And then how do I find the corresponding Y value for this 3? 1 here, here, and here. Okay, so that gives me 3 cubed, which is 27. That's 3 times 3 times 3. That's 27. Minus 3 squared. Is it with or without parentheses, this piece here? Is this the same thing as this? Are these the same? No. One's -9 and the other's 9. They're not the same thing. So do I need parentheses? Do I need parentheses here or not? Actually, I don't think it matters. So actually, that doesn't matter. It doesn't even matter. Sorry. All right, what's that? 9. And then minus t, which is 3, plus 3. What does that become? What is it? 18? Okay. So what is my average rate of change? Yeah, it's 5. So that goes here. So Josh, how do I figure out what C is? Yeah, sign in, please. And Ava Rose, if you have a case to work on, that's what I want you to do now. Or if you have a case for debate to work on, that's what I want you to do now. And if you don't, then I want you to find something in an outside class to do. Okay, Josh, how do I find my C value? What's that? Say solve for T. How do I solve for T? Okay, so if I subtracted 5 from both sides, that would give me 3t squared minus 2t minus 6. Does that look right too? There are 4 ways. This is a secondary math 2 idea. This is a secondary math 2 idea. There are 4 ways to solve for a quadratic. What are they? We can use the quadratic formula. Yeah, we can factor. What else? We can complete the square, or we can graph. If I want to graph this, how would I do it? Desmos, but how would I plug that into Desmos? How would I plug this into Desmos? For an x-intercept, y has to be what? 0. What if I make 0 y? Then the solutions are where? On the graph. They're x-intercepts, yep. For an x-intercept, y is 0. If I substitute y in for 0, then my answers are the x-intercepts. Now, let's assume that this is a non-calculator based problem. So I can't graph. Then how would we solve for this? Is it factorable? Can we factor this? Yeah, I don't think it's factorable. So if it's not factorable, what are we stuck doing? Quadratic formula. Do you remember the quadratic formula? What's that, Chris? Nice, good job. Now the quadratic formula only works if we can identify correctly what our ABC values are. What are the ABC values? Yep, and we're going to take those values and plug them in. So we have x equals, I'll use a different color, negative b. I'm just going to use place, oh, that's not b, that's a negative b. I'm going to use placeholders in the form of parentheses, plus or minus the square root of b, negative 2 squared minus 4a, which is 3, c, which is negative 6, over 2a, which is 3. Does that look right? more or less. Okay, what do I do first? What is this? Yeah, so I have x equals 2 plus or minus 4. What is all of this? 4 times 3 is 12 times 6, 72. 72, what's this plus or minus 72? Yeah, because I have a negative times a negative, which is a positive, so that's a plus. Over 6. Now what? So I have 2 plus or minus the square root of 76 over 6. Can this be simplified anymore? How do we simplify a square root? Don't we do a, starts with an F? But we use a factor tree. So if I have 76, what times what gives me 76? 2 and 38. 2 is already a prime number. What about for 38? 2 and 19. Is it 19? Yep. And so what does that mean? What can be taken out of the square root? A 2, leaving what in the square root? 19. So what I'm given is a 2 plus or minus 2 times the square root of 19 over 6. Can this be simplified anymore? Okay, to get what? Yeah, that's the most simplified. So there you go. We have 2 answers. We have 1 plus or minus the square root of 19 thirds. Let's graph this. Am I going too fast? Is everybody caught up? Let's graph this. Okay, my original equation was, I'm just going to use x's. Ah, gosh. Y equals x cubed minus x squared minus x plus 3. We have this graph right here. And we found a point, what was that? The slope is 5. I found a no, let's find our average rate of change. Average rate of change, what was our slope? 5. So I have 0, 0, and 3. What was the corresponding value for 3? What was it? 3, 9, 18. 18. Okay, 3, 18. Uh-oh. What did we get when we played? Oh, it was 0, 3, right? Are those right? Okay, so we found, so we have, these are, so the average rate of change should be through these 2 lines. That would be y minus 18 equals 5. Our slope was 5 times x minus 3. Does that look right to you? From here to here? That's our average rate of change, that slope. And it looks to me like we have some point over here that would be our instantaneous rate of change at this other value here. In fact, we found 2 values. Do we have 2 values? One of those values can't be correct. One of these values is wrong. Which value is wrong?
Minus,
Why?
because it's not in the, part that's part of the equation.
Yeah, in the interval, yeah, right? We're limited, our interval is limited to positive t values. And so that negative would not be positive. So we only have one answer at 1 plus the square root of 19 over 3. We just have that one answer. Okay, so I do want to try to find to see if it looks more or less like, let's see, how would we find that? So we need to find, let's see. We know we have a slope of 5. And that 5, that we know what x is for that. Let's see. We know what our x value. I think I'll just make this a slider. I'll make that a slider. So we're looking at a point approximately here, right? Maybe here. Is this number here 1.741? Is that, how close is it to this? What is, sorry, what is this? Put this in your calculator. What do you get? I'm saying that C value is, it looks to me like it might be 1.741.
It's showing it's 1.786.
7, 8. You're saying 1.7. Let's move this in a little bit. Well, 1.78, yeah, it's not quite a tangent line because it goes through both of those points. 7, so 786, 1.786, yeah, so in between these 2 points. Okay. There you go. Let's do another one. This is going to be a yes or no question. If I'm going too fast, let me know. T hours. R of T gallons per hour. Zero, 9.6, 3, 10.4, 6, 10.8, 9, 11.2, 12, 11.4, 15. Ava Rose, welcome back. 11.3, 18, 10 point, it doesn't look like a 10. 10.7, 21, 10.2, 24, 9.6. I'm going to let you catch up before I ask my question. It's going to be a yes or no question. Is everybody caught up? Here is your question. It's just a yes or no question. I want to know if there is a value of t in our interval from 0 to 24 such that r prime of t equals 0. Yes, no, maybe so. Is there a value of t in our interval from 0 to 24 such that r prime of t is equal to 0? Emerson,
I think, yes.
you think yes? What's your logic? Or are you just guessing?
No, I think that I was just trying to visualize what the graphs would look like if I like an inverted parabola.
Okay,
So then there would be a point at which there isn't the slope is 0.
huh? So and I agree with you. The answer is yes. And in fact, when I notice, if I look at as this interval from 0 to 24, that the corresponding y values for 0 and 24 are what? The same. Do we have a theorem that says that if our y values for the endpoints are the same, then that guarantees that there's a point where the derivative is equal to 0? Do you remember what that theorem is called? Does it start with an R? Yeah, it's Rolle's theorem. Yeah, Rolle's theorem guarantees it. Yeah, because our R of t, or R of 0, sorry, our R of 0 equals our R of 24. What does this mean? Is that an X or a Y? It's a Y when X equals 0. What's this one? It's Y when X equals 24. Do these equal? What do they equal? 9.6. So because these Y values are the same based on Rolle's theorem, it guarantees that we have an R prime of t that equals 0. So because of this, Rolle's theorem guarantees it. Rolle's theorem guarantees it. Okay, the next problem is one of my favorite because I made it up. Ready for the next one, or do we have any questions? Sam, how do you feel?
Yes.
You good? Okay. An object is dropped from the roof of Highland High School. From a height of 30 feet. What is the velocity when it hits the ground? An object is dropped from the roof of Highland High from a height of 30 feet. What is the velocity when it hits the ground? Well, I'm going to give you an equation. Actually, I need to move this whole thing up. It looks like I don't see that I have any more room here.
Is that 9.8 meters squared, is that the acceleration speed or is that the?
That is, yeah, that's acceleration. And that's, isn't that meters per second?
Yeah.
What do we want? We want feet. So for Earth's gravity, we have two equations. We have S of t. What does S of t mean? What am I referring to? Position. I'm talking about position. So S of t equals negative 16 t squared plus v naught of t plus h naught. This is for feet per second. We also have S of t equals negative 9.8 t squared plus v naught of t plus h naught. What is this in reference to? Meters. That's meters per second. Which one makes the most sense for this problem? Yep. Why are these values in the front, these leading coefficients, why are they negative? These both represent gravity, either in terms of feet or in meters. Gravity is a vector. Gravity points in what direction? Down. So that would be that the negative is in reference to our vector pointing downward. Okay, we're going to use the first one. What does V naught mean? It's our initial velocity. What is H naught? Our initial height. So our equation, our position equation in this case, is going to be what? S of t equals negative 16 t squared plus what? 0. Yeah, because we're just dropping it. If I drop it, what if I take the ball and I throw it into the air? Is that going to be a positive or a negative velocity? It's going to be positive. If I throw it towards the ground, is that positive or negative? That would be a negative velocity. Now, if I drop it, I'm not imparting any force on the object. So this is going to be 0. 0 times t is just 0. That's gone. What's my initial height? It's 30 feet. Our initial height is 30 feet. Since you're taking your backpack, should I assume you're not coming back?
Well, I can sleep.
Okay, so this is going to be 30. Right, let's make sure we don't lose track of what we're trying to find. It says, what is the velocity when it hits the ground? How do I find what the velocity is when it hits the ground? Well, sure, we can factor it, but what are we finding if we factor it? What's the goal? Yeah. Well, I mean, there's not necessarily a first direction. So I think that if you say something that would inch us towards our goal, then we should just go ahead and do it. So what's your suggestion? Chris, what was your suggestion? So what's our goal? What are we trying to find by doing that?
Oh, you're trying to find the instantaneous velocity with Instagram.
Instantaneous velocity. Is this a velocity equation? It's not a velocity equation, it's a position equation. It tells me at any point, put in 0. Time is 0. This goes away because everything is 0. We're left with 30. 30 represents what? Not our initial velocity, our initial position. Our initial position is 30 feet high. This is a position function. So I'm looking for suggestions of how we can find the velocity when it hits the ground. Yeah, let's find the derivative. I think finding the derivative is a good idea because the derivative will change a position function into a velocity function. Okay, let's do that. So let's use green if it moves it. So I have V of t equals what? Negative 32t, and what's the derivative of 30? 0, so that's gone. Okay. Now I could just keep on plugging numbers into here, right? I could plug in 0 or 1 or 2 or 3 or 4, and it looks like the acceleration just becomes greater and greater. So how do I find out my velocity when the object hits the ground? Yeah. I wish Emerson was paying attention. So Emerson, what was the brilliant idea that Kata just had? We already found the derivative. She said, if this is our initial height. We don't want our initial, we actually want to find the velocity when the particle hits the ground. Well, how do I show when the particle hits the ground? Yeah, my final height is 0. So let's make our final height 0. In fact, we're finding an x-intercept, right? If I'm standing here 30 feet above the ground and I throw a ball into the air, isn't that an x-intercept when the ball hits the ground? So let's make our final height 0 and find out at what time the ball hits the ground. So we're going to use 0 equals negative 16t squared plus 30. When the ball hits the ground, or the object, right? The object hits the ground. How do I solve for this? That says group. How about ground? There we go. How do I solve for this? Negative 30 equals negative 16t squared, okay? Okay, what do I get when I divide by negative? I guess we could just leave it, right? Is that negative 15/8 or positive 15/8 equals t squared? And then we take the square root of both sides. Oops, wrong tool. Take the square root of both sides. Get rid of that. And then, actually, I'll leave that. And then that's just t, right? This is t. That's our time when the object hits the ground. So the answer is t equals the square root of 15/8, assuming that time is only positive. That's when the ball hits the ground. How is that helpful? Yeah, plug that into the velocity equation and it'll tell me, then what does it tell me? Yep, that's exactly what we're looking for. The square root of 15/8. What does that give us? Do you have a calculator? And Sophie is on her phone. -43.882. Do you know what the rule is with an AP class or AP calculus, what the decimal needs to be? It's 3. What's 2 more? It went 7, 8, so we'll round up to 8. Okay. What are my units? Yeah, feet per second. Good. Nice. That was Chris. Chris is brilliant. So, Sasha, how did we go from this question here of trying to find, we're given a position. So, well, we found our position function. How did we go from a position function to find the velocity when the object hits the ground? We took the derivative, so that gave us the velocity, and then?
We made it so that it was the object of the ground, so we made it equal to 0.
No, we actually went back to our position. For our position function, when that equals 0, that's when the ball hits the ground. So we found that our time was the square root of 15/8. That's when the ball hits the ground.
And plug that back into the-
Correct. Yep, that is what you do. Nice. Okay, next one. So a professional baseball player can pitch a ball at 100 miles per hour. That is crazy. If the ball is thrown straight up when does it reach its highest point? A professional baseball player can pitch a ball at 100 miles per hour. If the ball is thrown straight up, when does it hit? When does it reach its highest point? Emerson,
Thinking about how to like convert the equation. We need to change the amount of miles per hour instead of feet per second.
yeah, so if we're going to use our equation, let me use red. we're going to use our S of t equals, what was the equation for feet? Do you remember? Negative
-16 squared.
plus V naught of t plus H naught.
Yeah.
Okay. And I want to, since this is for feet per second, we need to convert this, just like Emerson said, we need to convert this 100 miles per hour. So this is actually a tool that I learned, this conversion method. I learned this in chemistry of all places. So I have a 100 miles per hour. Now I'm going to end with feet per second. That's what I need to, it needs to equal feet per second, which means I need to get rid of hours and I need to get rid of miles and replace them with feet and seconds. Now, I know that miles divided by miles is 1, and that's a way to cancel it out. And hours divided by hours is 1. We can cancel it out. So let's start out with hours at first. If I want to cancel hours in the denominator, then with my new ratio, hours needs to be where? In the numerator. So hours. And if I'm trying to convert to feet, to seconds, sorry, wrong units, to seconds, then I'm going to put seconds down here. So what's the conversion? 1 hour equals what? So we have 1 here. It's 60 times 60, because there's 60 minutes in an hour and 60 seconds in a minute, right? Does that make sense why it would be 60 times 60? Okay. So that's going to get rid of our hours. Let's cross hours out. So hours divided by hours is just 1. I need to get rid of miles and get feet in this equation somewhere. So I'm going to multiply by, well, where do I want miles? I need miles in the denominator so that numerator and denominator cancel each other out. Wrong, sorry. I want, oh, miles, yeah, miles here. So I have miles, and I'm trying to convert to feet, so feet's going to go in the numerator. So miles and feet. What's the conversion for miles and feet? Yeah, 5,000, oops, wrong tool. 5,280 feet per 1 mile. Now miles can cancel out. Miles divided by miles is 1. We're left with feet per second, which is what we wanted. Use your calculator. What do we get? How fast does the ball, how fast does a professional baseball player pitch a ball in feet per second? Okay, 146 feet per second. Now, my concern is that if we, because this isn't our final answer, right? We still need to go back and use this equation here. So we can get, if we start rounding early, we get what is called a rounding error. I don't want a rounding error. Is this exact or is it rounded? Hello? It is. Oh, hey, how's it going? Go ahead. Okay, so, all right, what do I do? What are we trying to find? What is our goal? I want to find not how high the ball goes. Emerson, Killing me. I'm not trying to find how high the ball goes. What am I trying to find?
How high up it is when it's at its point.
I want to know the time it takes, right? How long does it take for it to reach its highest point? Isn't it? So when does it reach the highest point? I want to know how long it takes. How many seconds? How do I figure that out? So this means what? What does this mean? Now that we were distracted by the phone call, what does that mean?
That's the original velocity.
Yeah, that's how, yeah, that's my original velocity. So I'm going to plug that into here. So I have, is that what I want to find? S of t is my original velocity. All right, so we have S of t equals negative 16t squared plus 146.6 bar, meaning it repeats, times t. What's my initial height? Yeah, 0 plus 0. It actually doesn't matter, right? Because this guy's going to throw the ball. It starts here. He throws it up, and I want to know how long it takes for it to reach the highest point. If he was standing on a, some type of elevated platform and threw the ball up, wouldn't it still take just as long to get up to the highest point? Yeah. And so that doesn't really matter. We'll just say 0 to make our lives easier. Okay, so what do I do now? Take the derivative. This is a calculus class. This is a calculus. I haven't done any calculus yet. So it makes sense that we would take the derivative. If I take the derivative of a position function, what does that give me? Gives me a velocity. So that gives me what? Six bar. Yeah. Yeah. So now what? I have two variables. What does this variable mean? Why would I set that to 0? Yeah, because my velocity is at stopped, right? It went to the highest point and it stopped and then reverses direction. Isn't that an extrema? What extrema is that? Yeah, that's an absolute max. So I have a 0 equals negative 32 t plus 146.6 bar. And then? Okay, that gives me negative 146.6 bar equals negative 32 t. And that gives me that it takes how long? How long does it take for us to reach that highest point? What's the rule in an AP calculus class? How many decimals? 3. 4.583 units, seconds. Yep. That's pretty impressive. So somebody throws a ball into the air, 1,000, 2,000, 3,000, 4,000. That's how long it takes for the ball to reach its highest point. That's a long time. Emerson, what's that?
That's only half.
Yeah. Yeah, because it still has to return. Yeah. So we're looking at about 10 seconds, right? You throw the ball in the air, it takes about 10 seconds for it to come back crazy. Okay, let's try to zoom through another one. So, yeah, here's my next example. If f prime of x equals x minus 1 times x plus the quantity of x plus 2 all cubed times x minus 4 to the power of 2, then at what values of x does f have local extrema? I still have you for 5 more minutes. So I'm given my derivative function. And I want to know for the original function of f, where I have local extrema and what type. Emerson.
Say when x is 0, right? Anytime like x is 0, you could have one.
So when x is 0?
I mean, yeah, sorry, when y is 0.
Yeah, well, when our slope is 0, right?
Yeah, when the slope is 0, so when you have like, whatever x is, makes it any one of those.
Wasn't this called the first derivative test? The first derivative test tells us our monotonic properties. Remember monotonic? Monotonic properties are where the graph is increasing or where the graph is decreasing. So what tool do I use? What is that tool? So I set this to 0. So I have 0 equals the quantity of x minus 1 times the quantity of x plus 2 to the power of 3 times the quantity of x minus 4 to the power of 2. What's the tool that I use to do the first derivative test to identify those monotonic properties? Starts with an S. It's a sign diagram. We use a sign diagram. What are my critical points for this sign diagram? Okay, 1. What else? -2. And 4. Those are the values that will give me 0 over here. So I have 0 equals 0, where my derivative indicates that I have a 0 slope, right? Okay, how do I know whether over here the graph is increasing or decreasing to the left of x equals -2? How do I know whether the graph is, for this interval here, whether the graph is increasing or decreasing? Like give me an example. All right, so we want to try x equals -3. X equals -3. When I plug x equals -3 into this first binomial, what do I get? Yeah, it's negative. What if I plug it into the second binomial? It's negative. What if I plug it into the third? What is it? It's always squared. It's positive. What is a negative times a negative times a positive? A positive. All right, how do I know what's happening over here between x equals -2 and 1? Plug in 0, right? So try, let's use Tourette again. Let's try x equals 0. When I plug in 0 here, is that positive or negative? It's negative.
Good afternoon, everyone.
Plug it into here.
Sorry for the interruption. We have a couple quick announcements.
Positive.
So we can get your attention.
Plug in here.
We had a couple
Positive.
drawings today for our ran away shop.
What's happening when x equals -2?
First
What's
up,
happening
our
here?
winner of our
It's
guitar,
a maximum, yeah.
Briella
X equals -2 is
Unit
a
number 262-437.
max.
Briella, come on down to the main office and get your prize.
What about
Winner
here?
of our headphones is Holland Richards, 245-921 is the student ID. Holland, come on down to the main office, get your headphones. Also, just we still have our winner from last week, Chick-fil-A gift card. Might be going against the state is Dylan Porcelman. Dylan, if you're here, come on in and get your prize as well. All right, couple minutes left. Oh, also, I wanted to give a big shout out to band orchestra for a fantastic concert last night. You guys did a great job. Really enjoyed the concert. Let's have a great holiday break, everyone.
I still have you. What's happening when x equals 1?
Girls game tonight. Make sure you're there.
It's a minimum.
Supporting your Lady Rams. Varsity 7 o'clock, taking on West. Okay,
What's happening here when x is 4?
What do you do? Everybody do a quick favor.
Stationary inflection.
Run your classroom.
Is a stationary inflection an extrema?
Great, be safe.
No, it's not an
See you
extrema.
on January 3rd.
Are these local or global? So the first part, our graph is positive, 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 then negative, and then positive, 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 positive. They're only local. Both of them are local. They're both local. One other thing, hold on a second. The last thing on your homework, you're going to be given a function such as, I don't know, something like this. Actually, let me rewrite this. Something like this. And you have to find the derivative of this. How do you do it? The first step is find your zero slopes. Okay, what's the next step? Yeah, what's happening in between these two 0 points? Is the graph increasing or decreasing? Decreasing. What about on the right side of that zero slope? Increasing. What about on the left side of this zero slope? It's what? Increasing. So that should be what our graph looks like this.